here U is a finite dimensional vector space, so therefore we can choose the dimension of it. So let dimension of U is equal to n and dimension of nt is equal to k. We can choose because nt is a subspace of the domain space U. As the domain space is a finite dimensional, then nt is also a finite dimensional. Okay, so therefore we can choose dimension of nt is equal to k. Let set A is equal to u1 u2 up to uk, okay, be a basis of the null space nt. Okay, since nt is a subspace of U, okay, so this the A is a basis of nt, so set A is a linearly independent set. It is containing k vectors, and since the dimension of U is n, so we can extend this set A to a basis of U containing exactly n vectors. So we can extend, so we can have there exist some vectors uk plus 1, uk plus 2 up to un belongs to U, such that the set B containing vectors u1 u2 up to uk plus 1 up to un, this becomes a basis of U. Okay, so now take set C containing the vectors t of uk plus 1, t of uk plus 2 up to t of un. If I show that the set C is a basis of the range space T, then obviously this set C is containing total n minus k vectors, and if I show C is a basis of RT, then dimension of RT becomes n minus k. So we can write k plus dimension of RT is equal to n, and since k is our dimension of nt and n is dimension of U, okay, then this will prove the result, our theorem. So our target is what? We have to show that the set C, okay, is a basis of the range space RT. So to prove this, okay, first let we have to show that C is a linearly independent set of vectors. For this, take linear combination of vectors of C. So let alpha k plus 1 times t of uk plus 1 alpha k plus 2 times t of uk plus 2 plus up to alpha n times t of un, let that is equal to theta dash, because t of uk plus 1, t of uk plus 2 up to t of un, okay, they are all vectors of the codomain space V, and theta dash is the zero vector of the codomain space V. Okay, suppose this linear combination is equal to theta. If we show that these all scalars alpha k plus 1, alpha k plus 2 up to alpha n, they are all 0, then it proves that C is a linearly independent set. Okay, for this, since T is a linear transformation, so we can write these as T of alpha k plus 1 uk plus 1 plus T of alpha k plus 2 uk plus 2 plus up to T of alpha n un is equal to theta dash implies T of alpha k plus 1 uk plus 1 plus alpha k plus 2 uk plus 2 plus up to alpha n un, that is equal to theta dash implies now T is a linear transformation. Okay, this shows that T of this vector is becomes theta dash. Okay, now this we get this alpha k plus 1 times uk plus 1 plus up to alpha n un is equal to theta, because T of theta is equal to theta dash. So these vectors uk plus 1 uk plus 2 up to un are vectors of the set B, and B is a basis of U. So these vectors uk plus 1 uk plus 2 un are linearly independent vectors. So we get alpha I is equal to 0 for every I where k plus 1 is less than equal to I, less than equal to n. So we have taken the linear combination of the vectors T of uk plus 1, T of uk plus 2 up to T of un. Okay, for which we obtain that all the scalars in that linear transformation which equates the theta dash, they are all 0. So this way the set C is a linearly independent set. Now we show that C spans the range space RT. C spans the range space RT. Okay, that is, we have to show that span of C is equal to RT. Okay, so here C the set C is equal to T of uk plus 1 up to T of un is a subset of RT. Subset of RT implies span of C is subset of RT. Say result number 1. Now we show that RT is a subspace of span of C. To prove the equality, we show that RT is a subspace of span of C. For this, let us choose a random vector V belongs to RT. So V is equal, we can write T of U for some small u belongs to U. Now as U belonging to U and the set B containing n vectors u1 u2 up to un is a basis of the domain space U of T, then we can express U as a linear combination of vectors of B. So we can write down T of alpha 1 u1 plus alpha 2 u2 plus up to alpha k uk plus alpha k plus 1 uk plus 1 plus up to alpha n un. Okay, as U is a vector of U and u1 u2 up to un, they are all the vectors of the basis of U. So as since T is a linear transformation, then we can write down these as alpha 1 times T of u1 plus alpha 2 times T of u2 plus up to alpha k times T of uk plus alpha k plus 1 times T of uk plus 1 plus up to alpha n times T of un. As since T of u1 as since u1 u2 up to uk they are all vectors of they are all vectors of the null space of pages, please. Okay, as u1 u2 up to uk are vectors of the null space T, then T of u1, T of u2 up to T of uk, they are all theta dash. So this equals that alpha 1 times theta dash plus alpha 2 times theta dash plus up to alpha k times theta dash plus alpha k plus 1 T of uk plus 1 plus up to alpha n T of un. So this gives alpha k plus 1 T of uk plus 1 plus up to alpha n T of un. Okay, obviously this is a linear combination of vectors T of uk plus 1, T of uk plus 2 up to T of un, and they are all these all vectors of the set, okay, C. Okay, so we can say that this belongs to span of C. So we have chosen V belongs to RT random, and we have shown that this vector V belongs to span of C. So obviously RT is subset of span of C by definition of the subset. Say this too, from 1 and 2 equality follows, that is we from 1 and 2 we get C is equal to, span of C is equal to the range space RT. So this way we have shown that the set C is a linearly independent set, and it is also spanning the range space RT. Therefore, okay, we can say that the set C, is equal to T of uk plus 1, T of uk plus 2 up to T of un is a basis of the range space T. Therefore, we can say that dimension of RT is equal to the number of vectors in the set C. Obviously we have n minus k vectors in set C, because it starts from uk plus 1, uk plus 2 up to un. So n minus k vectors. Okay, so therefore we can write down k plus dimension of RT is equal to n. Now what is k? K is our dimension of nt plus dimension of RT, and what is n? N is dimension of u. Okay, so this proves the rank nullity theorem. We can write this as n of t, this as r of t is equal to dimension of u. Okay, so rank nullity theorem is proved here. It says that if u is any finite dimensional vector space, okay, and t from u to v be any linear transformation, then dimension of nt plus dimension of RT is equal to dimension of u. Okay, we move to the next one. Here we take one example. Okay, if t from R3 to R2, where t of xyz is equal to x minus y plus z, x plus y minus z, for every vector xyz of R3, then we can find the we have to find that nt, RT, the nullity of t, and the rank of t. Okay, so here we have given that t from R3 to R2. It is defined as T of xyz is equal to x minus y plus z, x plus y minus z for any vector. So first of all we find the nt, finding nt. Okay, so let T of xyz is equal to theta dash. Okay, then we find this vector xyz, so that will belong to the null space of T. So by definition of T of xyz is what? X minus y plus z, x plus y minus z, and it is equal to theta dash, where theta dash is the 0 vector of the codomain space R2. So it is equal to 0 0. So equating this, we get x minus y plus z is equal to 0, so equation number 1, and x plus y minus z is equal to 0, so equation number 2. So here we have to solve these equations for x, y and z. Since we are having 3 unknowns and we have only 2 equations, so any of 2 can be expressed in the form of third one. So now if we add these 2 equations, if we take 1 plus 2, so obviously this gives 2x is equal to 0. It means x is equal to 0. Okay, so putting x is equal to 0 in 1, we get y is equal to z. Okay, so our vector xyz, for which we get T of xyz is equal to theta dash, it is nothing but xyz is equal to, what is x? 0, y, and what is z is equal also y, where y belongs to R. So we can say that this vector belongs to the null space nt, then it is of the form 0 y y, where y belongs to R. So we can say that nt is the set of vectors 0 y y, where y belongs to R. So we can write these as 0 1 1, okay, times y, where y belongs to R. So we can say that the null space